Okay, this video is a reminder of what we did in year 12 regarding stationary point work. What I'm going to do is take an equation of a curve and I'm going to say let's work out the stationary points on that curve, and then once we've determined what the stationary points are, what their coordinates are and what type of stationary point they are, we will draw a sketch of the curve. So if I want to find the stationary points, we work out dy by dx. We work out dy by dx using the power method. 4 to the front, power goes down by 1. Plus 3 to the front multiplies the 4 to give 12, power goes down by 1. Remember, any number, positive or negative, if you differentiate it gives nothing. Remember, this is the gradient function, and you know at stationary points the gradient must equal 0. So we put that equal to 0 at stationary points. That phrase there is very important to write down. Okay, so what we end up with is that is equal to 0 for the stationary points. This is a little equation which we can solve, and that will give us the x values where the stationary points exist. So notice we've got an equation which we can now simplify by sharing by 4. So that's x cubed. We share that by 4, you get 3x squared. And you must also share that by 4. Don't forget to share that by 4. You get this equation coming out. It's a different equation to this equation, but it gives you the same answers, and it's easier to work out because it's got smaller numbers than the one above. So we're now going to solve this equation. It's a cubic equation, so technically it may have 3 answers. And you may need to try factorising the left-hand side in some of these questions using the factor theorem, either by the coefficients method, possibly, or by the long division method to get the factors. However, this is much easier because it's actually a common factor. Common factor of x squared inside the bracket equals 0. To get inside the bracket, x squared times x gives you x cubed, plus, and then x squared times 3 will give you 3x squared. So there's the factorisation. Now we say either the first thing equals 0, or possibly the thing in the bracket, x plus 3 equals 0. Now this one here will give you your first answer. X equals minus 3 is a point which has a stationary, which is a stationary point. This one here will give our second answer. Now technically this is an x squared equation, so there could be 2 answers. But because of the nature of this particular question, if we now just square root that, you square root the other side, yes, you would get plus or minus, which technically is 2 answers, but because it's 0, there's only one unique answer. X equals 0 is one answer. So even though it's a cubic equation, there are not 3 stationary points in this question. There are only 2. Let's work out the y coordinates to go with these x values. So we've got the actual point itself, which we can plot later. So if x is 0, go back to the curve now. So we go back to the curve, and everywhere you see x, you replace it with 0. So 0 in there, 0 in there, so y will simply work out to be minus 6. You can do that very easily in your head. So there is the point 0, minus 6 of the first stationary point. Okay, second, a bit harder to work out, so a bit more work involved. If x is minus 3, y will be minus 3 to the power 4. I'll actually write the substitution. Plus 4 lots of x cubed, minus 3 in a bracket cubed, take away 6. So let's work this out. Minus 3 to the power 4 is a positive answer of 81. Now be careful with this. This means you cube the minus 3 first to give minus 27, and then you multiply afterwards by positive 4. So I think that's minus 108. And then you subtract 6. You work that through, I think you get an answer of negative 33. So the second stationary point is minus 3, minus 33. What we need to do now is decide what type of stationary points they are. So a reminder of what we did in year 12. And you work out the second derivative to determine their nature. So you go back now to where dy by dx was. Now dy by dx was this expression. Be careful. It's that expression, not the line below. The line below, remember, was a simplification to help us get to this solution to the equation. But the actual dy by dx was that expression there. That's what you must use. So to get second derivative, we now differentiate again. 3 to the front and multiply the 4 to get 12. power goes down by 1, plus 2 to the front multiplies the 12 to get 24, power goes down by 1. So it's x to the 1 or just x. So there's the second derivative. We now look at the first point when x is 0. When x is 0, the second derivative will be 12 lots of 0 squared plus 24 zeros. That's 0. And if you remember the rules about the second derivative, what we've said in year 12 is that this must be a point of inflection if it's 0. I will say to you, technically that's not correct, and when we come to year 13 work and one of the future videos, we need to add a little bit more information about this. But for now, point of inflection from year 12 basis. Okay, next we look at the other stationary point, x equals minus 3, which is that there, and we work out the second derivative. The second derivative here will be a little bit harder, but not too bad. Minus 3 if you square it is 9, times by 12, that's positive 108. Plus 24 times negative 3, that's negative 72. That leads to a positive answer. You don't need to work out what the exact answer is. As long as it's positive or negative or 0 is all you need to know. This will be a local minimum from what you should know from year 12. Right, so we've now worked out the two stationary points and we know what type of stationary points they are. So let's quickly do a sketch of this situation. And it is only a sketch, so it's not a scale picture. 0 minus 6, so 0 on the x-axis, minus 6 on the y-axis. And that's a point of inflection. Now at the moment I don't know which way it's going, because it could be doing this sort of thing, or it could be doing that sort of thing. So for the moment I won't do anything else, just plot the point. Next, minus 3, minus 33, so something like this, go to minus 3 on the x, go somewhere down here. For minus 33, just mark on approximately minus 33, it's only a sketch. That's a local min. Mark on minus 3 there. That's a local min. So just, you can start that off because you know it must look like that. Right, well we've now got enough information to draw the picture, because this curve must obviously carry on up there because there are no more stationary points, so it can't be looping back on itself with a max or whatever. And if that is a point of inflection, the only way that can be true is if it's going up here like so and doing that sort of thing. And there you go, and it carries on upwards forevermore. So there you go, you've got 2 points of inflection. And one further point for you to be aware of, that this point of inflection here must go that way. It can't go the other way. I think that's self-explanatory. I won't confuse the issue. Okay, and that's in a nutshell the work that we did in year 12. And as a basis for what follows in the next few videos, you've got to understand those basic principles.